Hey guys, Chili here. In this video, I'm going to announce the winners of the Coding Challenge 3, the RoboMaze Exploration Challenge, and then I'm going to show you guys my solution and then maybe show off some of the submissions. Now, didn't get a lot of submissions for this one, and I think we can divide the reasons up for that into two main categories. Some people may have seen this and said, "Oh, this is super simple. I'm not even going to bother with it. It's just the maze. You know, you follow the maze, you keep the wall to your left-hand side, and eventually you'll find the exit." And that is not how you solve this one. If you tried that, you're not going to get a very good result. So that one can basically be chalked up to lack of imagination. Now, the other group is the people who understood, the challenge, that it wasn't that simple, but that assumed that it was way too complex and they wouldn't be able to solve it because it needs some kind of pathfinding. And I think that's also, it's not a very good mind space to be in, because as you'll see from my solution, it's actually not too complicated to solve if you just, think it through. But we'll see. Maybe you think differently. First things first, let me announce the winners. So I got 6 submissions, and Jojo 1000. I made a random maze generator, and I ran everyone's submission over 100 mazes. And Jojo was the only one who was able to solve them all. Dustin was able to solve a large majority. And then these guys down here, I believe they all did the wall following algorithm, which means they had a pretty low percentage. Now, Warrior Mario is a little weird because his crashes, so he's got a bug in there somewhere, and I couldn't really evaluate it. But when I looked at it, when I just ran it on like a single maze, I found that it looks like his logic is pretty solid, and it would probably get a good score if he had managed to fix the bug. So I'm going to put him, right around the middle here. But anyways, let's take a look at the solution. All right, so here's my bot in the maze here, and you can see that the tiles that it doesn't know about are all grayed out. And you can see here the 3 tiles that it sees at the start are not grayed out. Now, the basic idea of how you solve this is you want to explore the entire maze. So what you want to do is you want to keep moving to undiscovered tiles until you have discovered the entire maze. And as soon as you discover the goal, then you want to move there. It's pretty simple. Now, how are you going to do this? Well, you got to keep track of what tiles have been discovered and what tiles haven't. So what I do is I make a grid that basically is the same as the map here. And whenever I move, I get some vision on tiles, and I use that vision to update my internal grid inside my bot. And that's all you need to do. And then when you are deciding where to move next, you use that grid to find the next place to move to. Now, there's 2 problems that you're going to run into on this, and they might be able to stop you unless you think about it a little bit. So the first problem you might think of is, well, I don't know the size of the map. And so I don't know how big to make my grid. And the answer is, well, you know how big the maximum size of the map is. I specified that as maximum 1,000 by 1,000. So all you need to do is make a grid that is 1,000 by 1,000, and then you'll be able to fit any map in there. Now, one thing you might want to do is you could start off with a smaller grid and then grow it as you reach the boundaries, so dynamically grow your grid, and that would be good. But remember, in the specification for the problem here, I told you that you've got a gigabyte of memory to work with. You don't have to min-max the memory usage, so just allocate a huge grid. Now, another problem that you're going to have is you don't know where you're starting. So you don't know where the start position is, where to start drawing these in the grid. So if you assume that you start at the top left-hand corner, but you're actually starting here, then once you try to move to the left, in your own map space, you're going to be off the side of the map. So that's no good. How do you solve it? Well, you make your grid, your internal grid, twice as big as it needs to be in both dimensions. So make it 2,000 by 2,000. And now, no matter where you start, and then you assume you start in the middle of your grid. So no matter where you start in the actual map, your grid will always fit the map will always fit into your grid space. So you just allocate even more memory. And again, it might seem wasteful, but you got all the memory in the world, so keep it simple. A lot of things, or no, I wouldn't say a lot, but at least one person who I saw trying to solve this, they kept making it more difficult for themselves when all you needed to do was just be simple. That's the main thing of being an engineer, simplifying things as much as possible. But anyways, so you make a grid, you make it really big enough to hold the biggest map no matter where you start on that map. And then you just assume that your dude is starting in the middle of his grid. So he's going to start drawing the map in the middle of the grid. That's step one. Now, another thing that you don't know that throws a little uncertainty is you don't know the direction that you're starting in. So when you're drawing your map, when the guy moves forward, you don't know whether he's moving up on the map or whether he's moving right on the map. But again, that doesn't matter, because think about it. Any map, you turn it sideways, it's still a valid map. So if all you have to do is assume that your dude starts facing up, and then even if he's facing right, you're still going to get the right map. It's just going to be rotated, but it doesn't matter. It's all relative. So that problem that you might perceive is actually a non-issue if you take a little time to think about it. So anyways, yeah, that's what we're doing. We're going to draw a map, and we're going to, inside of our robot is going to draw a map in his mind, and he's going to use that map to basically explore the entire maze. Now, how this works is, well, let me just step through a little bit here. So he does a little, how you're going to see it. I have to move forward a little bit here. So let's just move forward, and you can see how the algorithm works, sort of. And once we get to an interesting place, then I will explain it a little more. But you can see he's proceeding here, and he is exploring unexplored tiles here. So when it hits a red place, that means that the search algorithm has found a tile to move to, and then it just starts moving there. Now, when we hit a dead end, I hope we can hit a dead end here, then you're going to see a little backtracking. Okay, I think we'll get to a dead end maybe here. Okay, this is good. This is good. So let's stop. Let's just step forward here. Now watch what happens when we have to backtrack. You can see what it's doing is it's basically growing out the region of tiles. It's visiting all these tiles in its own map, and I'm marking the tiles on the actual map as I visit them. And it's looking for a tile that it hasn't visited yet, or that it hasn't explored yet. And when it finds one that it hasn't explored, then it finds the path to that, and it goes to it. Now, how it does this is basic Dijkstra, I don't know how to pronounce it, but Dijkstra algorithm, right? So Dijkstra, it's super fundamental algorithm for doing all sorts of stuff in computer science. You should learn Dijkstra, okay? So if you don't know Dijkstra, I recommend you look it up. But if you want an idea of how it works, just look at this animation, because this shows you how it's working. It just keeps growing out from neighbors. So we visit a tile, and we add it to the group of visited tiles, and then we keep taking tiles out of the visited group and adding all the neighbors, like this. Then we move to the place where we want to go. I keep clicking the wrong thing. So now we are growing out our thing of visited tiles. We just keep growing out. So next one's going to grow to here. Now this one's it adds this one to the group of unvisited neighbors. It's going to grow to there. Now we have two neighbors that are unvisited, so it's going to grow here and here, there and there. Now we've got neighbor here, 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 and here, so it's going to grow to them. That one, that one, that one, and then it finds one that hasn't been discovered yet, so now it regenerates the path. Basically, in the Dijkstra algorithm, you kind of leave a trail of breadcrumbs. And then once you've found your destination, you can just retrace through the breadcrumbs to get your path. And then we're going to move across that path. So that is basically how it works. There's not really anything else to it. It's just you keep track of the map inside of your robot's mind, and then you use Dijkstra to find the next place to go to. And if we speed this up a little bit, you can see him. He's just going to keep searching until he finds that answer. You see, he got so close, but he missed it there. And there you go. He found it, and you are at the goal. And that is how you do the exploration. So you can see here, it's not trivial, but it's also not incredibly complicated. Let me show you the code. So I named my robot dig slide, and it runs from line 52 to line 260. So it's about 200 lines of code. Not really that big of a deal. I coded, well, I mean, this has gone through a few iterations. I had to solve a couple of problems, but I coded up the basic version that worked in about maybe 50 minutes, 40 or 50 minutes. And then I had another 10 or 15 minutes to debug it. So I got something working up in around an hour on this one. And then I had to extend it basically to work with any map size. Because before I just hard coded the width and the height into here. But I wanted to make it work with any map size up to 1,000. So I had to do a little extra. But yeah, and how it works in the code, let me see here. Well, I mean, I've got a grid. Let me see if I can find the grid. So the grid is just a vector of nodes, and grid width and grid height is there. Vector of A2, this is the path once it is done, finished its Dijkstra algorithm. It stores the path in this vector. Direction, angle. Okay, angle is not needed. I could have just deleted this. Direction is just the direction of the robot, the direction that it thinks it is in, and it starts off always thinking it's pointing up, even if it is not. So what are we going to do here? Let me just give you a quick overview. So the at function is what I use to look things up in the grid, and it translates between 2D coordinates into the 1D coordinate in my vector of grid. Now the grid, every node on the grid, contains information about the tiles, and it also contains information for the Dijkstra algorithm. So TT type is the type of the tile in the actual map, and they all start off invalid. Invalid here means it has not been visited yet. Now previous, this is the breadcrumb that is used for Dijkstra, and cost is also used for Dijkstra. And yeah, some functions here that are used for Dijkstra, like update cost and clear cost, get previous. These are all for Dijkstra. Set type is used for when you discover a tile and you want to update your internal map. And visual in it. This seems wrong. I'm on the wrong one here. This is the one. It's almost the same though, but you can see here that the angle isn't in here and some other things aren't in there. But yeah, there's at. So what does it do? Well, to start off, it pushes something up into the path so that the algorithm has somewhere to start. And it reset extents. I'll talk about extents in a second. So the plan is, this is what runs the overall, well, this is what gets the next move for the bot. And well, first off, if we're standing on the goal, then so it checks the map, its internal map, and if the place where we're standing, our position in the internal map, is goal, then we just return done to signal that we're done. Otherwise, we update the map with whatever view that we have. So we're given a view every time we make a move, we update the map with that. Then we check to see if we have revealed the target unknown square. So there is going to be a square that we are trying to move to, probably going to be an unknown square, and we just check to make sure, path back get type is. So if we reveal the square, the path is the path that we're going to be moving across to get to our target, and the last thing on the path, the back, is the target position. So if that is not invalid, that means that we must have already revealed it. So then we're done, and we should compute a new path. So if we have not yet revealed our target, then we compute the new path. And if compute path returns false, that means we have explored the entire maze, we have not found the goal, so we should return done to signal that we think that the maze is unsolvable. But if we have not yet revealed the target, then all we do is we find our position in the path sequence, the next place to move to, and then we call move to move to that position. And all that move to does is, first it rotates us to orient us in the direction we should be facing, and then if we are facing in the right direction, it moves us forward. So that is the basic overall of plan. Now the meat of the program is in compute plan, because this is where the Dijkstra is actually handled. And in here, we have the fun frontier. That is the frontier of nodes that we want to visit. We clear all the costs for the map. Reset extents, I'll talk about that later. We clear the path, and then we add the current tile to the frontier. So current tile that we are on goes into the frontier, and we update the cost of the current tile that we are on to 0, because it costs us 0 to move to the place that we're standing at. And then while we have stuff in the frontier, we remove something from the frontier. So what we're doing here is we've got a loop, and so base is the place, the tile that we want to visit. And when we visit a tile, we're going to add all of its neighbors to the frontier. So what we do is we start with a direction pointing up. We add that direction to the base tile, and that will get the tile, its neighbor above it. And then we check that neighbor to see if it is an unvisited tile, invalid, or it is the goal. And if it is one of those things, then we have found our new target, and we reconstruct the path to the target. Otherwise, we're going to update the cost to that tile, and if the cost is less than the current cost, then we add it to the frontier of new things to visit. Now, all tiles, when we, when we clear costs, we are setting all the tiles to infinity, basically to the highest cost possible. And so that is the first time we visit a tile, it'll be guaranteed to be added to the frontier. So yeah, that is how you do that. You just keep adding all the surrounding tiles to the frontier if we haven't looked at them yet. And once you find a target, which is either an unvisited tile or the goal, then you are going to push that back into, what are you going to do? Your construct path. So the node position, what is this? That's the base plus the direction. That's the current tile that we're evaluating. That'll be the first thing in the path. And then you are going to walk the path, the breadcrumbs, back to the beginning and push those all into the path. Now the path you get is going to be reversed, so you reverse that, and then you get the path and you return true. Now, if you make it outside of here, basically, if you remove everything from the frontier and you still haven't found a target, that means you can't reach the goal, you return false. So that's the basic idea of Dijkstra, but it's not going to make much sense just looking at it like this. It makes a lot more sense if you watch the animation of it actually happening. So I mean, here you can see we're adding new things. We're taking ones out of the frontier, we're adding the neighbors, and then once we find the target, we move to that, and then we rinse repeat until we find a target, and then we move to there. So most of the time, it's going to find the target right away because it's going to be close to an unvisited tile. It's just eating up unvisited tiles. But sometimes when it hits a dead end, it's got to backtrack, and then that's where the Dijkstra really comes into handy. But yeah, that's the basic idea. And then the debug version, it just does the same thing, but it it marks some things on the tile. It dims out all the tiles to start off with, and as you discover, it will undim them. And when it's running Dijkstra, it does it step by step. So here, every time it adds for Dijkstra, every time it adds something to the frontier, it's going to wait on tick, and that is what allows us to visualize the Dijkstra working as an animation. But it's the same algorithm in the end. Now, the one thing I did here was I had to add the extents here, which is just a rectangle. And the extents is for any one instance of calling compute path, I am going to have to reset all the extents in the entire grid back to basically infinity. Not the extents, sorry. Reset all the costs, clear the costs, which means setting them to the maximum integer value possible. And I found this to be excruciatingly slow because I had set my grid to be 2000 by 2000. So that's 4 million that it would have to set every time it computes a path. And that was slowing my program down a lot. So what I found was I don't have to actually clear the entire grid. I only have to clear the part of the grid that I touched in the last iteration. So I maintain this rectangle, visit extent, and that tells me the extent of the region that I had dirtied in the last run. And then when I call, for example, let me find it here, compute path, where is it? So now when I do clear costs here, instead of looping through the entire grid, I only loop between the extents here. And that speeded me up a lot. It was a really huge difference. So very important. You don't want to have to clear that entire grid every time you compute a new path. Only clear the part of the grid that you dirtied. And there's other ways you could do this, perhaps more efficient, but this was simple enough and it solved my problems. Now I could make this algorithm a little more efficient. I called this guy dig slide because for the cost of moving, it assumes that basically the robot doesn't have to turn to move to any tile. So all the neighbor tiles, they have the same cost regardless of the orientation of the robot. Now, if I wanted to make this even more efficient, I would factor in the cost of turning in my compute path. But I found I didn't need to. I got good performance out of it either way. And, I've already spent a lot of time building this entire framework. I didn't have time really to min-max it. So there's room for improvement, but honestly, it's not necessary. This thing runs super fast. But yeah, if you're interested at all in artificial intelligence, in pathing, or just basically in, computer science, in being not just a code monkey, but actually understanding some computer science theory, I definitely recommend you look into Dijkstra and you learn it. You try to implement it yourself and you don't stop until you succeed. Then there are a lot of animations online. You can, of course, run this program and watch my animation. You can step through this program. I've also added a bunch of comments to it so you can review the code. But they're all online on Wikipedia. Everywhere there are lots of animations and resources on learning Dijkstra because it is a fundamental algorithm and you should learn it if you want to be a programmer. If you want to be more than, just a shit tier code monkey, you need to learn the basic algorithms like Dijkstra. You don't need to learn how to pronounce it because, I still don't know that. It doesn't matter. You just need to know the sound it makes when it takes a man's life. Now let's take a look at the programs of all of the competitors. So the winner was Jojo. So let's start with Jojo's. We're going to rebuild solution here. One thing I found was if you copy and paste source codes into there and then you just run it, it's not going to rebuild it automatically. You have to tell it to rebuild all. Otherwise you're going to have partials from other stuff. It's not good. It threw me for a loop for a while. Now, technically, Jojo did not satisfy the criteria for the project because this project does not build. And the reason why it doesn't build in the framework here is because he did something that you probably should never do, which is he specialized the hash template in the namespace std for a type that he does not have control of. So you are allowed to specialize hash in std for types that you have control of, but not for types like int that are under the purview of the standard library, and not for other types, because think about it. You can't specialize this thing, this hash of a2. You can't do it twice. And what I did was I specialized it down here. So by him specializing it here, causes it not to break, or causes the code to break, actually. And that's no good. Now you might say, well, Chili, the original code that you had didn't have this specialization. So his originally would have built when he was developing it. But after I improved this for the testing purposes, I added this specialization, caused his code to break. But here's the thing. You can't assume that just because the maker of some API or some library didn't add this specialization before, that they won't add it in the future. So you can't assume that and start adding your own specializations for types that you don't have complete control of. And you don't have control over this because it's part of my API. So you should not add this specialization. Now, second thing here is this hash combination. He's combining two hashes with exclusive OR. That is actually a very bad idea. It's not a good way of hash combining. It works. The algorithm will still work, but it's a bad hash. So I'm going to comment that out. I will allow to use this because he's the only guy who managed to solve all of the maps. So he's still hats off to Jojo. Just gonna blow up his spot a little bit. So what he did was, instead of doing the grid like I did, he used maps and sets, which you can also use. All right, this looks a little more interesting. The goal is up here. Let's just run the dude and see what it looks like. So the purple is I don't know what the purple is, but it's the frontier of where he is not gone yet to move to. I don't know. Is it a bunch of places that you want to move to when you're done or something? So maybe he caches the location of goals, and then when he has to backtrack, he can just backtrack to that. I don't really know what he's doing here, but that looks like it might be it. I don't know, but you can see here. So his visualization here is just showing the parts that have been discovered and the parts that haven't been discovered. That's mostly what you're seeing here. That purple might be some caching of goal nodes, because you can see backtracked right to that one there. So yeah, that's cool. And if we run this faster, you should be able to make it to the goal. There it is. There you go. Beautiful. So there you go. That's that. Nice visualization. Not bad. I like it. There's your winner. Next up is Dustian. He got 90 out of 100. Lots of warnings in here. Tut tut. But still got a good score, so can't shit on him too hard. Let's see. What does his visualization do? So visualization just shows, oh no, it doesn't just show what has been visited or what has been moved to, but it seems to show something similar to what JoJo's was showing. Maybe. It's doing some weird stuff here. This isn't really a super efficient motion that we saw here, but it seems to be getting the job done. Let's speed it up. Why? I don't understand why they're being turned gold after being turned blue. It's an interesting thing. I'm going to say that. I don't really understand what's going on, but maybe he would like to comment on that in the comments of this video. But it works. It's a good job. It's all good. I like it. Now, like I said, Warrior Mario, his would end up crashing on certain maps. So when I ran the full suite of 100 maps, it would always crash at some point. I tried a few different seeds, couldn't get it to work. So I don't have a number of his success rate. But what we can do is look at his algorithm in action in one case here. So here we can see again, basically the visualization is just showing us where we have visited and what we want to visit next, maybe. So we're not seeing the actual running of a single search algorithm. We're just seeing the steps. But still, it's nice to have a little visualization. I approve of that. Yeah, managed to find it pretty quickly here too. Not bad. Of course, that's always what path it takes is pretty much random. But who knows? Like the simplest thing of just moving to the closest unvisited place could be augmented with some very advanced things. Like, for example, you could analyze the map that your robot has built and look at all of the things and try to determine maybe this is the extent of the map here, and you could use that to do some statistical analysis to determine where would be the best place statistically to look for the goal. I'm not exactly sure how that might be done, or maybe if it's even possible at all, but it's an idea. I think it would be possible, but in general, the routes that you choose, it's going to be random as to how fast you find the map. It just determines whether you happen to start off moving to the left or to the right when you are exploring the maze, whether you're going to find it quickly or take a long time. All right, and the last thing I want to show you is just what happens when you do like the wall following rule, what problems you can run into. So here is bot a submission. I will leave the name of the submitter anonymous to protect their identity. But here's what happens when you do the wall following. You just get a ring around the rosy. They can only follow along the walls, and if the goal is in the middle of a room, they will never be able to get the goal. Sometimes the wall follower can get lucky and the goal can be in a nice place and they don't get caught on a ring around the rosy. But in general, it's just not going to cut it. So you need to use a more advanced technique, and in general, you need to internally map that maze. You need to have, your robot needs to draw its own map and then navigate its own map in its own brain. And that's the fun part of the challenge. Now, I'm going to tell anybody still watching the video at this point, I really recommend that you try to implement this on your own now, because doing so will give you some very important skills that you need as a programmer. And you might say, well, what's the point? I can't submit it. I can't get recognition. It doesn't fucking matter whether I say your name in a video or not. All that matters is that you do it and that you get the experience and that you learn a skill. And I'll give you another reason why you should do it, because this isn't the end. This is only the beginning. I am going to be issuing other challenges in the future that are more advanced than the current one. This was the simplest challenge that I could think of that gives us the ideas of pathfinding plus exploration. Not just dumb pathfinding where you can see the entire map, but actual exploration where you have to draw the map yourself in memory. This is the simplest one, but I can think of many more interesting variations, more advanced situations that build on this basic starting point. And if you want to be ready for that future challenge, you should implement this challenge on your own and get it working. And then maybe you'll be in a good place for when I issue the next challenge. End of story. TLDR, last words. Motherfucking just learn Dijkstra. Okay, just learn it because you need it. And if you don't know it, freaking learn it. I mean, the stuff I showed you, the algorithm, you don't need advanced C++ techniques or anything. If you can do arrays, you can make a grid, a two-dimensional grid, and you can do Dijkstra. There's nothing else to it. There is nothing else to it. There is no excuse not to try to learn it right now. So get on that and then complete this challenge. You've already seen the solution. There's no excuse. You might say, well, I already seen the solution. I understand it. I know. But no, unless you've actually done it yourself, you don't know shit. Because once you try to start doing it, you're going to realize how little you know. So until you've actually completed it and coded it up yourself, you can't say you know it because you don't know it. All right, enough lecturing. I hope you enjoyed this video. I hope you learned something. I hope I managed to light a fire under at least a couple of your asses, get you going and actually doing this stuff yourself. And if you like these challenges and you want to see me make a new one, you want to see a new RoboMaze challenge, a new programming challenge, click that like button and that will get it to you faster. And I will see you soon with some more C++.